Ever try to find like a specific book in a library
Yeah.
with zero organization?
Yeah.
Like just piles and piles of books everywhere. Talk about a nightmare.
Yeah.
Luckily, in the digital world, we have hash tables to keep things from like descending into total chaos.
Yeah, it's a great analogy. Hash tables are all about bringing order to data, much like those library catalog systems we rely on.
Right, and that's what we're diving into today. The ingenious world of hash tables, recursion, and algorithms.
Hmm.
These concepts are like the hidden gears behind like how computers think. And once
Right.
you understand them, you start seeing their influence like everywhere.
You're absolutely right.
Um,
They might seem like, abstract computer science concepts, but
yeah.
they have a huge impact on our kind of daily digital lives.
So let's start by kind of unpacking hash tables.
Okay.
What are they in a nutshell?
Well, think of a hash table like a super efficient way to store and retrieve information.
Okay.
You mentioned a library catalog. It's a bit like that. Imagine having a key, like the book's title,
Huh?
and a value, which is where to find it on the shelves.
Okay.
Hash tables work in a similar way, using these key-value pairs.
Okay, that makes sense. But how does the computer actually find the right, like, shelf for
Yeah.
each piece of information?
That's where the hash function comes in.
Okay.
Think of it as a special librarian with a secret formula.
Okay.
They take the key, let's say the word apple,
Hmm?
and you use this formula to calculate a unique address, the shelf,
Right.
where that information is stored.
So it's like assigning each word a specific spot based on a calculation,
Yes,
not just like alphabetically.
you got it. And the source material had this really simple example that helps illustrate it.
Okay.
Imagine our hash function assigns both the letters A and B to the same index, like index 1.
I see where you're going with this.
Okay,
What happens when you need to store both apple and banana?
right.
They both start with letters that map to the same index.
That's exactly right. It's the classic collision problem,
right.
when two different keys get assigned the same spot.
Right.
But don't worry, computer scientists are clever. They've come up with solutions like chaining to handle this.
Okay.
It's like having multiple shelves at that same index to store kind of related information.
Clever indeed. So beyond organizing our digital libraries,
Yeah.
where else do we see these hash tables in action?
Oh, they're everywhere. Compilers use them to keep track of variables, which is essential for your computer to understand and run code.
Right.
Even the DNS system,
Okay.
the one that translates those website names we type in, like google.com,
Right.
into actual computer-readable addresses that relies heavily on hash tables.
Wait, so every time I go online,
Yeah,
hash tables are working behind the scenes to make sure I end up on the right website.
exactly. It's like a digital phone book, connecting those human-readable names to the specific locations, those IP addresses of servers around the world.
That's mind-blowing. I never realized how fundamental hash tables are to just like browsing the web.
And it's not just basic browsing. Even search engines like Google,
Mm.
while their exact methods are top secret,
Yeah.
almost certainly use hash tables extensively.
Okay.
Think about how many web pages, images, and videos Google has to index hash tables, help them organize that massive amount of data
Right.
so that when you search for something, they can find it in a fraction of a second.
Okay. That's officially blown my mind. And to think we're just getting started on our deep dive.
It is pretty incredible when you think about it. The
Yeah.
sheer scale of data being like shuffled around behind the scenes
Right.
every time we're online.
Yeah.
And speaking of clever organization and problem solving,
Yeah.
that brings us to our next topic, recursion.
Okay.
It might sound intimidating, but it's a really elegant way that computers tackle problems.
Recursion always makes me think of those Russian nesting dolls,
Uh-huh.
where each doll contains a smaller version of itself.
Yeah,
Is that on the right track?
that's a perfect analogy.
Yeah.
Recursion is like that it's a function that calls itself,
Okay.
but with a slightly smaller version of the problem each time.
Okay.
Just like those dolls eventually have a smallest one that doesn't open.
Right.
Recursion needs a base case to tell it when to stop.
Right.
Otherwise, it would just keep going forever.
Otherwise, the computer would be stuck in an endless loop of nesting dolls, not very efficient.
Right, exactly.
Our source mentioned the factorial example as a classic use of recursion.
Yeah,
Can you break that down for us?
absolutely.
Okay.
The factorial of a number is represented by that exclamation mark in math.
Right.
And it means multiplying that number by all the whole numbers less than it, down to 1.
Okay.
So 5 factorial, written as 5,
Right.
would be 5, 4, 3, 2, 1, which equals 120.
Okay.
Now, the cool thing is that the mathematical definition of a factorial is naturally recursive.
Okay.
The formula for n is simply n times n1.
So the code for calculating a factorial using recursion almost writes itself.
Precisely.
Wow.
You have your base case, which tells the computer that if the number is 1, the factorial is just 1.
Okay.
Otherwise, it multiplies the number by the factorial of the number minus 1.
Okay.
It's a remarkably concise way to solve what seems like a tedious calculation.
That's pretty elegant, using the problem's own definition to solve itself.
Yeah.
The source also mentioned the Fibonacci sequence in connection with recursion.
Okay.
I'll admit that one always kind of trips me up.
The Fibonacci sequence is fascinating.
Yeah.
It pops up in all sorts of unexpected places.
Really?
It starts with 0 and 1,
Okay.
and each following number is the sum of the two before it.
Okay.
So you get the sequence 0, 1, 1, 2, 3, 5, 8, and so on.
Okay.
What's really wild is that this sequence, which seems so simple,
Yeah.
appears everywhere in nature.
Wait, really?
Yeah.
Tell me more about these Fibonacci appearances in nature.
Oh, it's everywhere.
Wow.
From the arrangement of petals in a flower to the spiral patterns in a pine cone or the shell of a nautilus.
Wow.
There's even a connection to the golden ratio,
Really?
which is often found in art and architecture.
Yeah.
It's like nature has a favorite mathematical sequence that it uses over and over again.
And this sequence can be defined recursively as well.
Exactly.
Okay.
Just like the factorial, it has a beautifully recursive definition.
Okay.
The base cases are that the other Fibonacci number is 0 and the first is 1.
Okay.
Then any other Fibonacci number is the sum of the two Fibonacci numbers that come before it.
Okay.
Very elegant way to describe this kind of naturally occurring pattern.
So we've got these recursive functions breaking down problems into smaller, self-similar pieces.
Yeah.
Is that kind of what the divide and conquer strategy is all about?
Yes.
Okay.
You're exactly right.
Okay.
Divide and conquer is like a core problem-solving approach in computer science.
Right.
And it ties in perfectly with what we're talking about.
Yeah.
Instead of tackling a huge problem all at once,
Right.
you break it down into smaller, more manageable chunks,
Yeah.
solve those individually,
Right.
and then piece together the results.
It's kind of like that saying, how do you eat an elephant? One bite at a time.
Exactly.
Yeah.
Our source breaks divide and conquer down into 3 main steps.
Okay.
First, you divide the problem into those smaller subproblems.
Okay.
Then you conquer those subproblems by solving them independently.
Right.
And finally, you combine all those solutions to get your answer to the original bigger problem.
So it's like a strategic approach to problem solving rather than just like brute forcing your way through it.
Precisely.
Okay.
And this strategy is incredibly powerful for a whole range of tasks.
Yeah.
We're talking sorting huge amounts of data,
Right.
searching through information quickly,
Yay.
even doing really complex calculations.
Wow.
It's everywhere in computer science.
It's amazing how much efficiency comes from just approaching a problem the right way.
Yeah.
Speaking of efficiency and clever problem solving, the source mentioned the Towers of Hanoi puzzle.
Right.
I've always been fascinated by that one, but I'll admit, I don't fully get how it works.
Ugh. The Towers of Hanoi. It's the classic.
Yeah.
You have 3 pegs and a stack of discs of different sizes on one peg,
Okay.
with the smallest at the top and the largest on the bottom.
Okay.
The goal is to move the whole stack to another peg,
Right.
but you can only move one disc at a time.
Right.
And you can never put a larger disc on top of a smaller one.
Okay. I can see how that would get tricky pretty quickly, especially with more and more discs.
It definitely gets complicated.
Yeah.
In fact, the legend goes that the puzzle was originally posed with 64 discs.
Okay.
And with 64 discs, it would take an astronomical number of moves to solve it, like 18 quintillion moves.
18 quintillion, that's practically impossible.
Exactly.
Yeah.
But here's where divide and conquer and recursion come into play.
Okay.
If you only have one disk, it's a single move, right?
Right.
That's your base case.
Okay.
With more disks, you break it down recursively.
Okay.
You move the top N1 disks to the auxiliary peg.
Right.
Then you move the largest disk to the destination peg. Finally, you move the N1 disks from that auxiliary peg to the destination peg.
Okay.
And you repeat those steps for each smaller stack until you're down to single disk moves.
So we're essentially applying that same strategy again and again,
Yes.
but to smaller and smaller stacks of disks.
Exactly.
It's like that Russian nesting doll idea coming back again.
You've got it.
Yeah.
And what seems impossibly complex with 64 disks becomes manageable when you break it down recursively.
Right.
Of course, no one's going to sit there and physically make 18 quintillion moves.
I was just thinking that. But the idea that we can use these elegant methods to conceptualize and solve problems that seem impossibly large is Pretty amazing.
Absolutely.
Now, are binary search and backtracking also examples of this divide and conquer strategy?
Yes, they are.
Okay.
Yeah, it feels like we're about to go down another rabbit hole of fascinating computer science concepts.
So we're back to divide and conquer, using that elegant strategy to break down big problems
Right.
into smaller, more solvable ones. And you mentioned binary search and backtracking as two prime examples.
Yeah.
To be honest, those sound a little intimidating.
They might sound complex, but they're actually quite intuitive once you grasp the basic idea.
Okay.
Let's start with binary search.
Okay.
Imagine you're looking for a word in the dictionary,
Oh.
but instead of flipping through page by page, you use a smarter strategy.
Okay.
You open the dictionary right in the middle
Okay.
and see if your word is alphabetically before or after the words on that page.
Okay, that makes sense. So you eliminate half the dictionary right away.
Exactly. And you keep doing that,
Right.
dividing the remaining pages in half
Right.
and narrowing down your search until you zero in on the page with your word.
Right.
It's much faster than a linear search, especially when you're dealing with a lot of data.
That's way more efficient than my usual method of flipping randomly and hoping for the best.
Yeah.
So how does backtracking fit into this divide and conquer idea?
So backtracking is like a systematic trial and error approach, often used to explore different possibilities within a set of constraints.
Right.
The source material uses the classic 8 queens puzzle as an example.
Okay.
You ever heard of that one?
It rings a bell, but remind me how it works.
Sure. Imagine a chessboard.
Okay.
The challenge is to place 8 queens on the board so that none of them can attack each other.
Okay.
That means no 2 queens can be in the same row, column, or diagonal.
Okay. I can see how that would require some serious strategic thinking.
You got it. And backtracking provides a method to navigate all those possibilities without getting totally lost.
Okay.
You start by placing a queen on a square.
Okay.
If that placement leads to a conflict where one queen could attack another,
Right.
you simply backtrack.
Okay.
You remove the queen from that position and try a different square.
Right.
It's like exploring a maze. Sometimes you hit a dead end and have to retrace your steps to find a new path.
So it's like a choose your own adventure for algorithms.
Exactly.
Yeah, if a choice doesn't work out, you go back and make a different one.
Right. And while it might seem like a lot of trial and error,
Yeah.
backtracking is actually very systematic.
Okay.
It's guided by the rules of the problem
Right.
and the idea of undoing incorrect choices to explore all valid solutions.
Right. So this is used in a lot more than just chess programs.
Oh, all over the place.
Really? Like where?
Think about online navigation systems.
Okay.
They use backtracking to find the shortest route,
Huh.
exploring different paths and backtracking when they hit a dead end, like a traffic jam.
Right.
Or in artificial intelligence, where a program might need to backtrack to find the best solution to a complex problem.
It's amazing how these concepts we're talking about, these problem-solving strategies, are applied in so many different areas.
It really is. And speaking of clever organization and efficient problem solving,
Yeah.
that brings us to our last topic today. Binary trees.
Okay, binary trees are those like regular trees,
Exactly.
but with ones and zeros instead of leaves.
Not quite, although the analogy to a tree structure is pretty spot on.
Okay.
Instead of branches and leaves, we're talking about nodes and connections.
Right.
Imagine a family tree
Okay.
where each person is a node
Uh-huh.
and the lines connecting them represent their relationships.
Yep.
Binary trees are similar. They're a way to organize data hierarchically.
So instead of a family tree, it's like a data tree.
Exactly.
Right.
You have a root node at the top.
Right.
And each node can have at most 2 children,
Okay.
often referred to as the left child and the right child.
Okay.
Now, there are different types of trees. Generic ones and array trees where a node can have more than 2 children, and binary trees where the maximum is 2.
Okay.
But they all share this branching structure that's incredibly useful for organizing and accessing data efficiently.
So it's like taking a huge,
Right.
potentially messy pile of data
Right.
and organizing it in a way that makes it easy to find what you need.
You got it. And there's a particular type of binary tree that's especially cool.
Okay, what's that?
The AVL tree,
AVL tree.
named after its inventors.
Okay, and what's so special about AVL trees?
AVL trees have this incredible self-balancing property.
Okay.
It's like having a tree that automatically rearranges its branches to stay perfectly balanced, no matter how much data you add or remove.
Wait, so if you keep adding data to this AVL tree,
Yeah.
it reorganizes itself to stay balanced?
Yeah,
How does it even do that?
through series of clever rotations.
Okay.
Imagine a mobile hanging overhead. You had a weight to one side.
Right.
It tips over.
Right.
AVL trees use rotations, which are like shifting the weights on that mobile
Okay.
to ensure that the tree stays balanced even as data is added or removed.
It's so clever. So it's constantly adjusting
Yes,
to maintain this balance.
exactly.
Why is that balance so important?
That balance is key because it makes searching for a specific piece of data within the tree incredibly fast.
Okay.
Imagine trying to find a book in a library where all the books are just piled haphazardly on the floor,
Right.
versus one where they're neatly organized on shelves in alphabetical order.
Okay, that's a no-brainer. The organized library wins every time.
Right.
So AVL trees with their self-balancing act are like the perfectly organized library of the data world.
Exactly. And these types of self-balancing binary search trees are used all the time in databases, search engines, and many other applications where you need to be able to retrieve specific pieces of information from massive data sets very quickly.
It's kind of amazing how like all of this stuff kind of works together,
Yeah.
you know?
Yeah, it's really fascinating.
Yeah, this deep dive has been quite a journey. We've gone from hash tables,
Right.
which are like those well-organized library catalogs,
Right.
to recursion, where problems elegantly solve themselves,
Yes.
to divide and conquer, which is like having a master plan for tackling any challenge.
Exactly.
And finally, to these amazing self-balancing binary trees that keep our digital world running smoothly.
I know. It's amazing.
You know, it's really cool stuff, and I really hope that our listeners out there really
Yeah.
enjoyed kind of going on this journey with us today.
Me too. It's been fun.
Yeah, this is great. And for our listener, next time you're searching for something online
Mhm.
or using a navigation app or like even just opening a document on your computer,
Right.
remember this. Behind those like seemingly simple actions, there's a whole world of like ingenious algorithms and data structures
Yeah.
working tirelessly behind the scenes.
Working hard.
Right. You might be surprised by how much your appreciation for the digital world grows when you understand a bit of what's going on beneath the surface.
Absolutely. I agree.